minus 108. Well, actually, from where the place I get this number is some, it says it's not minus 13.6, it's minus 13.604. So from there I get this number. Okay. The experimental value for helium is indeed, experiment tells that this is minus 79.01 electron volts. Well, actually, the experiment is only the first ionization energy of helium, which means what is the energy that is required for the electron to go from helium to continuum, to outer space, right, to vacuum, and how much energy, and that is for the first electron that goes out. For the second electron, it becomes like a hydrogen-like, and for the hydrogen-like you can get an exact solution, right? So add these two energies up and you get minus 79.01. Okay, which means that we are at a gross error. I think the error it says is I don't know, 38% or something. You could do that calculation. So definitely I need to include the interelectronic repulsion terms. So what do I do then? I say fine, let me define a guess function, let me make some guess, right? Because whatever I do, see, minus 108 is much lower an energy than minus 79, right? So if I make a guess function which is well behaved, I will get it always more than minus 79. That's the variational principle, right? So let's make a guess function. Now, the guess function that I make is that tell me. No, nothing? You can share the joke, no problem. The guess function I make is that I put both of these electrons in psi1s, okay, and use the hydrogen-like orbitals psi1s as guess functions. So I use exactly these wave functions as guess functions, but now I am not using only this particular Hamiltonian. Let me call this huge thing. So starting from here and going all this way, let me call this H0, and let me call this small part as H prime. Well, although these terms I am taking from the perturbation theory, but I am not going to discuss perturbation. So in perturbation, what you write is one unperturbed, one undisturbed Hamiltonian, H0, and you treat this small thing as a disturbance, a perturbation. But anyway, I can always write my Hamiltonian H is equal to H0 plus H prime. That's not a problem. So psi1s into H0 plus H prime star. So I put both the electrons in 1s, right? You know from the Pauli principle that you can accommodate two electrons in one level. And then I do a psi beta, right? I can break this up into two different problems since we are using linear operators. Psi star 1s square H0 psi beta, which we've just seen the solution is minus 108.83 eV, and plus psi star 1s square 1s 2 whatever H prime, which is nothing but E prime square by R12, which takes care of the interelectronic repulsion term. So I take that and I put it over here, and psi of same thing beta. Now both my electrons are sitting in the 1s orbital, right? This is the first term is H0 term is without the repulsion, and the second H prime term is the repulsion term. It's going to be a huge integral to evaluate, so I'll just tell you what the results are. it comes out to be 5 by 4 z e prime square by 2a naught. Okay. So if I put the value of z over here, it gives me 34.01. So the total comes out to be minus 108.83 plus 34. It's a repulsion term, so this is going to be positive. Plus 34.01. A repulsion interaction is a destabilizing interaction. So it's going to take the energy up, right? So what it gives me is minus 74.82 electron volts. And the experimental one is minus 79 eV. Okay. So the moment I included the interelectronic repulsion terms, but my guess function was the same 1s orbital for hydrogen, except that Z was included now. Right? So I get somewhere close, minus 74.82 electron volts. Although it's close, it is 5 electron volts. 5 electron volts is as good as a bond. So you will not be able to estimate any chemistry if you are off with this kind of an uncertainty. The error is roughly about 5.3% error. That looks very small, but it's not good. So I need to do something to improve upon it. So I'll just tell you one of the procedures today, and it's possible to improve it to nth degree of, nth place of decimal. It's always possible. Yeah, people have done calculations to show that it's correct up to 10th place of decimal. We'll not worry about that, but we'll worry about the concept that is here. And the concept is that, you know, the electron, there are 2 electrons in this helium atom, and if the nucleus is attracting 1 electron, then it does not have the entire positive 2 charge to attract the other electron. This is something that you know. It's, I guess the battery is going off. Never mind. So if you have this second electron, then it does not have a plus 2